If you learned math any time in the last few centuries, you probably did a lot of this. Pushing around numbers and letters inside an equation until an answer pops out. It's math with the alphabet, the bane of every high schooler's existence. But solving for x the way we know it has a complicated history. And to see where it all began, we can follow the trail of written progress backwards. Until that trail ends here, with this scholar. He's writing a practical manual of arithmetic for judges and merchants. But then he goes further, laying a foundation that would be passed down for centuries and would one day make the modern world possible. The scholar is Mohammed ibn Musa al-Khwārazmī, and his book was known for short as al-jabr, algebra. But all those symbols that we take for granted would have been considered absurd 1,200 years ago.
It's a semiotic monstrosity which nobody would have ever thought of.
So where did this first algebra book in history come from, and why does it look so strange to us today? This is a story in 3 parts, and it begins during a time of lavish government funding for science. By the turn of the 9th century, the Abbasid Caliphate was arguably the largest empire in the world, and its leaders had started a massive project to collect and translate the great works of ancient wisdom from within its borders and beyond. Literature and philosophy from Persia in the northeast of the empire, astronomy and arithmetic brought by visiting scholars from India east of the empire, and Greek philosophy and mathematics from ancient texts, some of which had long been held by Christian scholars within the Caliphate. In the middle of this sprawling, multi-ethnic empire were the Tigris and Euphrates rivers. And between these rivers, on the banks of the Tigris, was Madinat as-Salam, the city of peace, also known as Baghdad. This capital of the empire was only a few decades old, but it was already the largest and richest city in the world. Protected by a giant moat and a massive circular brick wall, the architects of the City of Peace must have known that Baghdad's future wouldn't always be peaceful. While some claim that the circular layout of the city was a tribute to Euclid, the great Greek geometer, that is unlikely, because even though Euclid's work was already 1,000 years old, the first Arabic translation of the Elements didn't appear until at least a decade after Baghdad's founding. But this landmark work from the ancient Greeks would cast a long shadow over the emerging discipline of algebra. See, today, we know basic algebra as a powerful general system for finding answers to a wide range of problem types using the efficient manipulation of symbols which represent variables and undetermined values. Because we can do things like writing and solving general formulas and graphing functions, we use basic high school algebra all the time to model all sorts of phenomena from physics to economics. But for most of algebra's history, it was just a way to find unknown numbers. And every other part of what we think of as algebra came together gradually across different times and places. But all the while, lingering in the background, was the ideal of mathematical rigor set out in Euclid's Elements and its approach to axiomatic deductive reasoning. This is the idea that you can start with a few simple assumptions and build absolute knowledge bit by bit using proofs constructed in a series of logically undeniable steps. As long as you can accept the starting assumptions and you give a proof with no logical flaws, then a mathematical theorem is absolutely true. This approach made math, and specifically geometry, different from other branches of science and philosophy. But for algebra, whose focus for many years would be solving problems involving numbers, reaching this standard would face major hurdles. Within Euclid's Elements, books 1 through 6 and 10 through 13 deal with geometry, while books 7, 8, and 9 are about number theory. The categories are kept separate from one another because the rules for shapes and magnitudes are completely different from the rules for numbers. Geometric magnitudes are continuous, while numbers are made of discrete indivisible units, so they don't allow for things like irrational values or even fractions. And a proof that works within geometry doesn't necessarily also work for numbers. So in Euclid's geometry, he never gives anything in numerical measurement. This separation between the study of numbers and the study of geometry was a key pillar of ancient Greek mathematical philosophy. But if you wanted to build a house or calculate a financial transaction, picky theoretical distinctions between numbers and magnitudes don't really matter. This tension between being useful in the real world and meeting this idea of theoretical rigor would hang over algebra for centuries to come. But the scholars of the Abbasid translation movement would have also known about another tradition of far older math whose origins were much closer to home. And this tradition would ultimately give Al-Khwārazmī an intuitive way to demonstrate some of his algebra. Because scattered everywhere in the region, mixed in with the ruins of past cities from ancient Mesopotamia, were indestructible clay tablets that revealed the rich legacy of Babylonian math. These tablets were dug up and translated in the 19th century, but it's thought that these traditions survived into medieval Baghdad. This math revealed powerful techniques for solving complex problems, including those that we'd describe today using quadratic equations. Here's how it works. Let's say you've got a rectangle and you want to find its dimensions. You know it has an area of 39, and you know that its width is 10 units longer than its length. This tablet gives a problem with this exact setup, but I've changed the numbers to simpler ones. We start with a big rectangle whose area is equal to 39, and we break it into two pieces, a square with sides equal to the unknown length, and a rectangle which is 10 units wide by that same unknown length. And then we break the rectangle into two equal pieces like this. So now we've got two rectangles which each have one side with the unknown length and the other side with a length of 5. And if we rearrange them so they're attached to the sides of the square, then we get this L shape. And we can think of this shape as being like a bigger square which has a chunk missing. Because we'd split the rectangle in half, we know that that missing part is itself also a square with sides of length 5. And filling that in means we're adding 5 times 5 equals 25 to the total area. In other words, we've completed the square. Since 39 plus 25 gives us a total area of 64, this is an 8 by 8 square. And since we know that the sides of this square are equal to our unknown value plus 5, then the length of the unknown side is 3. This approach to problem solving is sometimes known as Babylonian cut and paste geometry. Today, we solve problems like this using modern algebraic notation, which can represent a general quadratic equation in the form ax squared plus bx plus c equals 0. Following this Babylonian completing the square method with our notation gives us the modern quadratic formula. Except we allow for negative numbers and the Babylonians didn't. But it would be a mistake to say that we can understand much of anything about how the Babylonians thought about their math by writing it that way. Because for them, this really was about cutting up shapes and moving them around to solve problems. Each tablet describes a different ad hoc solution to a different problem. And the idea that these relationships could be represented by general equations, and that these equations could then be solved by applying some kind of unified method, is nowhere to be found here. Not only that, but the Babylonians didn't write about practical uses for quadratics. There's no textual evidence here or within Greek mathematics of quadratic relationships being used to solve any real-world problems. One historian thinks that the Babylonians mostly studied problems like this to help the educated elite train their minds and develop problem-solving skills. Turns out that math teachers really have been saying the same things for 4,000 years. But we know that math is good for more than just mental exercise. And in Baghdad, if you knew where to look, you would find people doing practical math too. As difficult as it was for Abbasid scholars to track down ancient wisdom, these days it seems like you can find out anything about anyone online. My partner and I Googled our names recently, and we instantly found all kinds of personal data about our family. Phone numbers, past and current addresses, phone numbers and addresses of extended family, you name it. And that was just from a quick search. I'd never tried to scrub my data from the internet before, and I thought it would be a complicated process. So I was amazed by how simple it turned out to be with the help of this video's sponsor, Incogni. Incogni automatically and simultaneously searches hundreds of known data brokers, online directories, people search sites, and more for your personal information and sends takedown requests on your behalf. Then they stay with it over time, sending follow-up requests to ensure that removals stick, and continuously monitoring for new exposures so your information doesn't resurface. It's a hands-off system that takes care of everything for you. But if you do happen to find something that Incogni missed, then with the Incogni Unlimited plan, all you have to do is copy the link, drop it in the dashboard, and click Submit, and the team will start working on getting rid of that data immediately. It can't take things down from government sites or social media, but this is the perfect solution for easily getting your information out of the hands of data brokers. They can't harm you if they can't find you. Use code Syversen at the link below and get 60% off an annual plan. Back in 9th century Baghdad, the theoretical math used by Euclid and the Babylonians wasn't the kind of math that would be useful for people's daily life. If you wanted to find math like that, you'd have to look somewhere else entirely. Because as goods flowed into the city, merchants calculated prices for their wares, architects worked out dimensions for new constructions, and judges divvied up estates according to mathematical rules dictated by the Islamic laws of inheritance. And the practitioners of these time-honored trades were experts at the calculations required for their daily work. Skilled tradespeople could do powerful mental math, and when they needed to keep track of intermediate values for larger computations, they would have either used a technique called finger reckoning to record the big numbers, or they might have used Indian notation on an erasable dustboard. But the only reason we know about this stuff at all is because later scholars wrote about it. But the field of practical arithmetic included more than just the basic operations that we think of today. It also included problem-solving techniques that were used to find unknown values. One of these was called the method of false position. Let's say we know that a heap and its fourth is 15, and we want to find out the size of the original heap. We can start by choosing a convenient guess. Maybe we guess that the heap has 4 units in it. Then the heap plus a fourth of itself gives us 5 units. Now, that's the wrong answer to our question, because the number we're looking for is 15 units. But scaling up our heap by a factor of 3 scales the 5 up to the 15 that we're looking for. And that same scaling would mean the original value of 4 becomes 4 times 3 equals 12, which is the correct answer. Of course, in many cases, you'd need to scale by a fractional value. Depending on the profession, fractions and even irrational numbers like square roots were all fair game for computation, and had been since before ancient Greek times. These things obviously show up when you're trying to get stuff done in the real world, and there's no sense in getting hung up here with picky philosophical distinctions between numbers and magnitudes. These practitioners had other methods too, like another more sophisticated technique called double false position. This one originated in ancient China and used interpolation of 2 guesses to effectively solve any linear equation. And then for dealing with proportions, there was also a method known as the rule of 3. This one is basically the same as what you get today when you solve an equation using cross multiplication. But these methods all start with a known number or numbers and proceed forward from there. None of them actually involved naming and manipulating unknown values. This is what makes them arithmetic procedures instead of algebraic. But naming unknown numbers and then doing math to them would be the key first step towards what we think of as solving for x. And alongside these arithmetic traditions, there were methods for this too. As simple as they might seem to us today, these versatile building blocks will give algebra its power to solve a wide variety of different types of problems. Start with a balancing scale. Let's say that on one side we have an unknown quantity which has had 5 units taken out of it, and we know that what's left is equal to 3 units. By naming one or more unknowns that I'm going to do mathematical operations with, I've left the realm of arithmetic and entered the realm of algebra. I can restore the full value of this unknown by adding the 5 units back, and when I maintain the balance with the other side of the scale, I get my answer. I can also bring quantities of the same type to the same side of an equation to simplify. This is what's best translated as confrontation. Let's pretend we have 2 unknown things on this side and that they're equal to 1 unknown thing plus 4 coins on the other. If we confront the like terms on opposite sides of the equation to remove them, then we get our solution. These operations of restoration and confrontation were known as al-jabr and al-muqābala. Even though these ideas weren't new, they'd surely been floating around for millennia, The rules had never been explicitly named and written down in a book. Books were still the domain of scholars, and these methods had been passed down through the centuries within oral traditions, by tradespeople teaching the skills of their profession to the next generation. But oral traditions are fragile. If the practitioners of these methods were to dwindle in number, or if the lines of transmission were to somehow break, then these practices could be lost forever. And in 812, civil war came to the city of peace. The Caliph Harun al-Rashid, who had ruled the empire for over 20 years during a golden age of prosperity and culture, had died 4 years earlier, and he left the caliphate to one of his sons, Al-Amin. But Al-Amin was a weak ruler who felt threatened by his half-brother, Al-Mamun, who was next in line for the throne. So when Al-Amin tried to remove Al-Mamun from the line of succession, the ensuing conflict spiraled into a civil war, culminating in a year-long siege of Baghdad. By September of 813, Al-Mamun's army penetrated the city's walls, executing Al-Amin and taking the throne. But this wasn't the end of the city's troubles. The war had devastated the civilian population, many of whom lived outside of the circular walls, and Al-Mamun's newfound hold on power was initially fragile. Parts of Baghdad were in ruins, and the instability meant that the caliphate was beginning to lose its centralized authority over its sprawling empire. But gradually, Al-Mamun consolidated his power, and once he did, he sought to finish what his father had started, setting the empire on a renewed path of scientific inquiry. He accelerated the translation initiative, and he encouraged new scientific work to flourish. In doing so, he brought some of the empire's best and brightest scholars to Baghdad. This central role of Baghdad in Abbasid intellectual life is often credited to the House of Wisdom, though the implication that this was some kind of translation bureau or university is now thought to be a myth that was created later in Europe. But in any case, one scholar who worked in Baghdad was Muhammad ibn Musa al-Khwārazmī. Very little is known about al-Khwārazmī's life. We do know that he was of Persian descent, and either he or his ancestors came from Khwarezm, a remote but prosperous region which is now part of Turkmenistan and Uzbekistan. He was Muslim, but it's possible that he converted from Zoroastrianism. In any case, Al-Khwārazmī soon found himself working in Baghdad at the forefront of geography, astronomy, and astrology, not to mention mathematics. So when the Caliph wanted to codify the practical oral math that already existed in the streets and marketplaces of the city, he turned to Al-Khwārazmī. And while Al-Khwārazmī would do what Al-Mamun asked, to make clear what was impenetrable and make easy what was difficult, he had his own plans too. Because in writing his Manual of Algebra, Al-Khwārazmī would bring together the practical oral traditions of solving linear equations with the ancient theoretical techniques of solving quadratics into a single, flexible framework. And while this framework would give the template for teaching basic algebra for centuries, its emphasis on practicality also meant that Euclidean-style rigor would be forever out of reach. Let's take a look at the book itself and use modern language for a minute to talk about what's inside. Al-Khwārazmī's book is a textbook for solving linear and quadratic equations. Negative numbers and zero weren't acceptable as solutions at the time, and while terms could be subtracted from each other, Al-Khwārazmī catalogs his equations into 6 canonical types, where the only operations being used are addition. 3 are simple equations like this, which only have 2 terms each and are straightforward to solve. Each one gives a single solution that's greater than 0. Then there are 3 compound equations which have 3 terms each. Here, the terms are moved around so that there's no subtraction, and he only considers versions that can give a positive solution. For each of these, he gives an algorithm to solve the equation, followed by a geometric demonstration to show that his steps work. The next part of the book has a bunch of simplification rules, like how to expand binomials and how to do things like simplify square roots. But weirdly, despite the title of the book, he never directly explains the al-jabr and al-muqābala procedures in here. You have to pick that up from context, I guess. But that's not the only strange thing about this book. The structure itself is weird too. He puts the 6 equation types first and then waits till later to explain the more basic simplification rules, even though you need those to get your equation into one of the 6 types. It's backwards from how anyone would ever teach it.
Other later algebra books do present things in what we would call the proper order. You introduce the names of the unknown, you explain how operations work on them, you explain equations and how to simplify them, and then you get to the 6 equations and their solutions. Al-Khwārazmī doesn't do that. He starts with the 6 equations. And my guess, and the guess of some other people also, is that that was really his baby. He's very likely the person who classified those equations and came up with those proofs. So he wanted to put that in the forefront. And he put that right in the beginning.
This pattern of classifying equations and then giving the solution method for each one would become a template for centuries of later authors, even after they extended their methods to higher degree polynomials. Next, like any good textbook, he's got a bunch of example problems. These are set up so that you can use the simplification rules to reduce each equation down to one of the 6 types, and then you go to the beginning of the book and follow the steps for solving that type to get the solution. He starts with a bunch of general equation solving problems and contrived sounding word problems involving quadratics, and then he has chapters with applied problems from different disciplines like commerce, geometry, and the math involved with complex Islamic inheritance scenarios. But all of these applied problems are solvable with linear equations. He doesn't actually give any examples of applied quadratics problems. As useful as quadratics are for us today, even in Al-Khwārazmī's time, they were still basically just a theoretical exercise. Now, to Al-Khwārazmī, the way I've been describing everything here, using equations with variables and general coefficients like a, b, and c, would have made no sense. His book catalogs a series of rules and justifications for solving different equation types, but this algebra is still miles away from the algebra that we know, where letters are used to represent either variables or unknown constants, which gives us everything from a way to express general formulas to the ability to work with things like functions. In fact, those things would have been impossible in Al-Khwārazmī's time, for 2 very specific reasons. The first was the nature of books themselves.
People had a different relationship with books back then. That's what it is. Books were transcriptions of lectures. And you can have illustrations in the books, like in Euclid's Elements, you have diagrams. But the diagrams are not part of the running text.
Well, today a math book can use abstract notation to efficiently convey complex ideas that are difficult to recite out loud. At this time, aside from a few simple diagrams, everything in a book was written out in words, even the numbers. But this isn't to say that Arabic mathematicians never wrote down math in symbols.
Because they were using the symbols on a dustboard to work things out. But then if you wanted to communicate that calculation in a book, you have to write everything out in words. You have to describe it. That's what Al-Khwārazmī does. He describes the processes.
But the differences between medieval algebra and the algebra that we know run much deeper than just words versus symbols. Al-Khwārazmī would have considered it impossible to write a general quadratic equation because of something even more fundamental: numbers. Remember the Greeks and their careful separation of numbers from geometry? Well, part of that was because numbers in pre-modern mathematics didn't mean the same thing that they mean to us today. At this time, numbers weren't abstract things that just existed in and of themselves. There's no number 3 that's just out there floating around in the universe or existing on a number line. Instead, 3 is an adjective, which needs to modify a noun. You can have 3 rugs or 3 vases, but you can't just have 3 on its own. And you can't have a negative number of a tangible thing either. It's a little bit like how we use a word like dozen today. You could have a dozen eggs or a dozen bagels, but you would never say, think of the number dozen. So medieval numbers come in what's called quantity species pairs, and you need both parts for the syntax to make sense. This means that when it comes time to define our unknown numbers, what we call variables, they have to follow the same quantity species syntax.
For us, when we write something like 3x, the x stands for a number, the 3 is a number, and the 3 and the x are understood to be multiplied together, right? Well, in Arabic, when they said 3 things, things is not a number. Things is a kind of number. If I say $3, that's not 3 multiplied by dollars. 3 is just how many dollars you have.
Instead of just having some abstract number x floating in the ether, the unknown is a species, a specific unknown thing where you can then have some quantity of those unknown things. Al-Khwārazmī refers to his constant numbers using the unit of dirhams, which was a type of money, but here it just meant sort of a generic unit. Then he called his unknowns shay, meaning thing, and sometimes he also used the word jabr, meaning root. But then, squared unknown values were a different species of thing, so he gave these the term mal. Then the relationship between these three items becomes a little bit like the relationship between different denominations of currency. Just like you can have 8 pennies, 3 nickels, and 2 quarters, you have some number of dirhams, shay, and mal. The unknown shay works a bit like a mystery denomination, where we don't know its value, and then the mal is like a different denomination whose worth is equal to the shay multiplied by itself.
And for this reason, they could not have undetermined coefficients. This is a major consequence of this. Because, well, for us, if you look at the bx, the b and the x are both numbers, right? Well, if you're thinking about it in Arabic terms, like how many things do you have? You can't, there's no word or symbol to designate an unknown amount.
Remember, the unknown shay is a species, not a quantity. So the notation allows for describing an unknown species, but not an unknown quantity.
It's not just their notation, it's the whole way they conceived of monomials and polynomials. Their notation reflects their understanding. So if you wanted to say bx, you'd have to have a way to represent just the quantity and not the whole quantity species pair, because you can't have 10 units things. That's like saying 10 degrees dollars. It's a semiotic monstrosity which nobody would have ever thought of.
So instead of writing symbolic formulas using undetermined coefficients like we do, Al-Khwārazmī leads by example, giving specific sample problems that the reader would extrapolate to other situations.
It's very clear from the examples that he has a general rule, and he's explaining the general rule in terms of a particular example.
Al-Khwārazmī's case number 4 is a mal plus a root equal to a constant. For this one, he uses the example that we would write as x squared plus 10x equals 39. Here's a look at the procedure as he describes it. After he gives these steps, he gives 2 geometric demonstrations, one of which we've seen before, because it's exactly the same as the procedure that's described on that ancient Babylonian clay tablet. But Al-Khwārazmī can't just demonstrate completing the square once for this one example. His classification system has 3 different compound quadratic equations, and the first demonstration only works for the first case. So each of the other cases needs a new demonstration. Here's one more for case number 5 when the square and the constant are on one side and the unknown is on the other. Let's say we have a square plus 21 equals 10 times the unknown root. First, we'll construct a square whose sides are equal to the unknown, and then we can add onto it a rectangle with an area of 21. We don't know this rectangle's exact width, since the length of it is the unknown value. But what we do know is that since the length of this big rectangle is the unknown value, its total width must be 10. The next step is to divide this long rectangle in half, so each piece is 5 by the unknown length. Then we get this little margin, a piece of the rectangle that's been cut off and is on the same side as the square. Let's copy that little piece and move it up here to the top. The area of this L-shaped region is still 21, and the little missing region is a square whose side length is the same as this length down here. If we could find that length, then we'd be able to find our unknown. We know that this big shape is a square with an area of 25 because we know that this length plus the unknown is once again 5. That means that the area of the little square has to be 25 minus 21 equals 4. So this is a 2 by 2 square. If that bit has a length of 2, then we can find that our unknown value must be 3. Now, you might want to go through this demonstration using modern notation. If you do that, you'll see that in the end, we get the quadratic formula just like we did with the demonstration of case 4. But you might also notice a problem, because unlike the other example, this equation has 2 positive solutions. In fact, at the start, we assumed that the rectangle with the area of 21 would be wider than the side length of the square, meaning that splitting the figure in half would split the rectangle like this. But if we assume the other scenario instead, now the width of the rectangle is smaller than the side length of the square, so splitting the figure in half splits the square instead. With this setup, we can also get a valid demonstration and the correct second solution. While Al-Khwārazmī notes that you can get a second solution, it was up to other authors around the same time to actually write out the full demonstration for all cases. Now, to Al-Khwārazmī, the point of these demonstrations was to convince a practitioner, not a theoretical mathematician, that his techniques work. So the rigorous and complicated style of Euclid's Elements didn't serve his purposes, and he used the more intuitive cut-and-paste methods of the Babylonians instead. After all, Euclid needed 30 propositions, 4 definitions, 5 postulates, and 5 common notions just to build a square. Not only that, but Al-Khwārazmī is freely switching back and forth between the world of numbers and the world of geometry here. Remember that for the Greeks, the distinction between numbers and magnitudes was a foundational idea. Mixing discrete numbers with continuous magnitudes breaks everything. Later mathematicians would try for centuries to close the gap between Euclidean rigor and algebraic practicality, but in the end, this fundamental structural divide would be impossible to overcome. In the years that followed, Arabic algebra flourished, and subsequent generations of mathematicians made major breakthroughs. Abu Kamil expanded on Al-Khwārazmī's work. His book demonstrated examples using irrational coefficients and solutions, where Al-Khwārazmī's examples only used integers and fractions. Abu Kamil also tried to ground some of his rules in Euclid's Elements, but the tensions were apparent. Later, Al-Kharajī wrote Euclidean-style proofs for his algebra, but then he had to follow that book up with another shorter one that was more practical, because the Euclidean theory was too complicated for practitioners. Al-Kharajī also started a movement towards what we'd call the arithmetization of algebra, the idea that you can do the same arithmetic operations on unknowns that you can do with numbers. Not only that, but he laid out what we now know as the binomial theorem and what we call Pascal's triangle. Much later, Al-Samu'al expanded on Al-Kharaji's project. For example, he gave a rule for taking the square root of a polynomial with subtracted terms. And separately, Omar Khayyam used geometric methods to expand algebra, including classifying the 14 forms of cubic equations and using the intersections of conic sections to find their solutions. In all, the lineage of Arabic algebra formed a rich tradition that continued for the next 600 years after Al-Khwārazmī. But other than Al-Khwārazmī and Abu Kamil, none of this work would be known outside of the Arabic world until the 1800s. While the Abbasid translation movement led to a golden age of mathematical and scientific progress for the centuries to come, the early 9th century ended up being the high watermark for the Abbasid Caliphate itself. The end of Al-Mamun's reign marked the beginning of a slow decline of the power and reach of the empire. Less than 100 years after Al-Khwārazmī wrote his algebra book, the circular walls of Baghdad were completely destroyed. Today, no remnants of the ancient circular city remain. Modern historians can't even agree on exactly where it was located. But during the 10th century, the rival Umayyad caliphs in Spain had built one of the largest libraries in the world, and they'd sent emissaries east to buy books from within the Abbasid Caliphate, including the works of Al-Khwārazmī and Abu Kamil. After the fall of the Umayyads, 12th century Europeans discovered these books, and Al-Khwārazmī's algebra would be translated into Latin by Robert of Chester in 1145, and then later by Gerard of Cremona around 1170. By then, this math was totally outdated within the Abbasid Caliphate, but it would take Europe another few centuries to catch up to what Abbasid mathematicians had already accomplished. In 1202, Fibonacci wrote Liber Abaci, the first major European text on algebra and arithmetic. He had picked up this Arabic math in his travels, and his book used example problems from Abu Kamil, but his book didn't explicitly credit any Arabic mathematicians. At this time, algebra wasn't taught in the medieval universities because it was a practical tool for tradespeople, as exemplified by the Italian Abbasist tradition. Sometimes called the last of the Abbasists, Luca Pacioli published his Summa de Arithmetica in 1494. It was a comprehensive volume covering the 6 equation types from Al-Khwārazmī via Fibonacci, along with the methods of Italian Abbasists. Pacioli famously declared that the general cubic equation was unsolvable. But soon, mathematicians like Tartaglia, Cardano, and Bombelli found solutions to cubic and even quartic equations using novel methods like imaginary numbers. Throughout these years, numbers and monomials still referred to quantity species pairs, and different degrees of unknowns had names like Koza, Censo, and Kubo. So writing a polynomial still involved writing complicated, partially rhetorical expressions. And even though algebra was useful for finding the right answer, finding rigorous mathematical truth still meant doing Euclidean-style proofs with axiomatic deductive reasoning. That ancient division from the Greeks, holding that numbers and magnitudes were completely separate from each other, meant that numerical algebra would never meet the standards of Euclidean rigor. For example, geometric constructions were still the only way to rigorously handle things like irrational values. So in 1591, François Viète introduced the idea of making an algebra for geometry. He said that algebra had been spoiled and defiled by the barbarians, meaning Arabic mathematicians. He even tried to get rid of the name, calling it the analytic art instead of algebra. By tying his unknowns to geometric magnitudes instead of numbers, he was able to move algebra towards the status of a theoretical science rather than a practical art. But it still didn't resolve the fundamental issue of numbers versus magnitudes. In the process, Viète introduced the use of letters for both unknown and general coefficients. His work would set the stage for René Descartes, who first used superscripts for exponents, a, b, and c for known constants, and x, y, and z for unknown values. By the second half of the 18th century, Leonhard Euler's work expanded the capabilities of algebra, and in the process gave us the standardized notation that we still would recognize today. Although by today's standards, even Euler's algebra falls short of what we consider to be fully rigorous. Ultimately, Euclid's Elements would have to be abandoned altogether as the arbiter of rigor in favor of a new foundation based on abstract axioms that aren't grounded in the tangible world. But working our way forward through history like this doesn't really give us the full picture. We might be tempted to infer transmission and influence at times where none actually occurred. For example, Al-Khwārazmī was not the first person to ever write about doing algebra. Sometime around the mid-200s AD lived the Greek mathematician Diophantus. Not only could he solve quadratic relationships like the Babylonians did, but he had devised methods to work with indeterminate equations going up to the 9th degree. And for this reason, some consider him to be the founder of algebra. A few centuries after Diophantus, over in India in the 600s lived Brahmagupta. He used quadratic equations to solve problems related to astronomy. And even though he wrote out his methods in verse, his technique for solving a quadratic is essentially identical to today's quadratic formula. There's no evidence that Brahmagupta made any attempt to justify his rules with anything that looks like a proof. In fact, it's clear that both Diophantus and Brahmagupta were doing math that was more sophisticated than Al-Khwārazmī's math. But to understand the textual tradition, we shouldn't just look at a chronological series of events across the world and say that's how things happened. Instead, we should take a more forensic approach and try to reconstruct a chain of transmission. If we put a pin at someone like Euler, whose work looks basically like modern algebra, and trace our way backwards, we'll get a different picture. Many books during these years attributed the birth of algebra to Al-Khwārazmī, but sometimes they were confused about when he lived, even imagining that he preceded the ancient Greeks. Others said that Al-Khwārazmī shares credit with Diophantus, as well as a third guy named Jabr, sometimes Jabr the Arab. It turns out that Jabr was actually just a mistranslation of the word algebra. But when we actually trace which books influenced which, the paths all point back to Al-Khwārazmī, where the trail abruptly stops. Because within these lines of transmission, no book of algebra precedes Al-Khwārazmī's condensed book on calculation by restoration and confrontation. When we look at it this way, even Diophantus comes after Al-Khwārazmī. Because even though Diophantus lived about 600 years earlier, his work wasn't translated and read by Arabic mathematicians until about 870, a generation after Al-Khwārazmī. And Diophantus wasn't known to Europeans until much later than that, when the German mathematician Regiomontanus discovered the work around 1463. And even though Arabic scholars did receive astronomical texts from India, and they learned what we now call Arabic numerals from India, Brahmagupta's algebraic work wasn't translated into this lineage until later still. Indian mathematics continued to develop independently into the 16th century, with mathematicians finding things like the power series for sine, cosine, and arctangent over a century before calculus emerged in Europe. This tradition never spread out of southwestern India, and it seemed to abruptly die out when the chain of transmission from teacher to student atrophied. So, what do we make of Al-Khwārazmī the person? Besides the handful of his books that have survived and that went on to plant the seeds of algebra in Europe centuries later, almost everything about his life is completely lost to history. It's vanished alongside the remains of medieval Baghdad. But yet, Al-Khwārazmī's name and work has lived on, even beyond what I've described in this story. In fact, if anything, his name has grown in importance over the years, to the point where today it's hiding in plain sight, constantly at the tip of everyone's tongue. Because algebra wasn't Al-Khwārazmī's only important work. He also wrote another book on Indian arithmetic, which codified Indian numerals and methods of calculation for the Arab world. When this book was translated into Latin, it gave Europe what they later called Arabic numerals. The book opens with the phrase, "So said Al-Khwārazmī." In Latin, that's Dixit Al-Khwārizmī.
The algorithm.
The algorithm.
The algorithm.
The algorithm.
The algorithm.
Algorithm.
The algorithm.
The algorithm.
Algorithm.
The algorithm.
The algorithm.
The algorithm.